All right, hello everyone. I'm here to talk about nonlinear inversion and magnetic resonance elastography. So I'm more used to presenting my research to MRI people, and this is very different. So hopefully I'll introduce you a little bit to MRE. So we're starting with elastography. So if you've been to the doctors the last 3,000 years, they might have done palpation on you. So a medical doctor might describe this all fancy, but more or less they poke you in the belly to see if anything is stiff or if anything is bigger than it's supposed to be. And this is a practice that has survived for a long time, and it's quite efficient because you don't need any instruments. But it's quite subjective. It's dependent on who does it. And also, there's a bunch of organs that you can't poke, say the brain or the heart. So more objective methods have been developed. Shear wave elastography is one where you use ultrasound to assess the stiffness of an organ. But even using shear wave elastography, some organs are shielded by bone. An example is the skull, which makes it inaccessible for even shear wave elastography. So there you can use magnetic resonance elastography. So magnetic resonance elastography uses an MRI machine together with harmonic motion. This little GIF here is worth to note. This is exaggerated. Your brain doesn't shake this much. But the harmonic motion is oftentimes introduced by an external driver. So when we do on the brain, we place a little pillow under your head and then it shakes at around 50 hertz. And since it's harmonic motion, we can put this in the Fourier domain and then we get a complex displacement. So time is removed, which is very convenient. MRE was first used for liver diagnostics. And the liver is really nice because it's more or less just a big blob. You can make a bunch of assumptions that stay true. The brain is a little bit more difficult, and we'll get into that more. But we've seen that the stiffness of the brain can predict Alzheimer's, MS, and Parkinson's. You can also use it to plan how you would extract a tumor from the brain, which is convenient as well. So what I'm going to be talking about is something called inversion. So you have this time harmonic displacement field, which is really nice, but it doesn't really tell you anything about the actual tissue. So what you want is the material field, here denoted as theta. So there are multiple different inversions. Maybe it's not too clear, I don't know. But direct inversion was the first one that they did. So you more or less just take the governing equation, you impose it on the displacement data. And it's really fast and convenient, but it assumes local homogeneity, which holds true for the liver, but for the brain might not. And it also does differentiate noisy data, so it becomes even noisier. Recently, as with every other field, deep learning methods have emerged. They train either on synthetic data or already inverted data. It's fast and evolving, but it requires a lot of data or assumptions. And it's also very difficult to verify. So the method that I use is called nonlinear inversion. So it uses finite element modeling and also nonlinear optimization. It's very noise robust, and it's also more verifiable because it actually comes from physics. However, it is very computationally expensive, which becomes a hinder in a clinical setting. And the current implementation is done in Fortran and MATLAB, and is very inaccessible and is not being developed as much as previously. So nonlinear inversion works as here you have UM, which is the measured displacement field. So that's what you get out of the MRI, the displacement field. And then you do some initial guess on the material field. And this is usually something that's homogeneous, just as a first guess. You then use the measured displacement as usually a boundary conditions and simulate a synthetic displacement field here called UC, C for calculated. You then compare these two and you create an objective function that's more or less the distance between the two different fields. you have some preset tolerance for this value, and if it's not small enough, you use this function to update the material field. And then it goes around and around and around until the objective function is sufficiently small, and then you say that you've reached the field. So then the theta that you have is the theta of the material. So the material model is not that exciting. It's just isotropic linear viscoelastic. It's nearly incompressible. And since it's from MRI data, we generally use isotropic hexahedral elements. It's a quadratic for the displacement and linear for the material field. Yeah, so what I've done thus far is validating the forward simulation with COMSOL. And it's just like normal phantom geometries. I don't want to confuse you with this cute little GIF. There is no time axis, so the one to the right is like the actual data. But you do have displacements in X, Y, and Z, and also real and imaginary displacement. I also did mesh convergence to see how many nodes per wavelength I need to have sufficiently low error corresponding to the MRE signal. And found that the value of around 15 to 20 is probably good. So for doing the actual nonlinear inversion, you can do a little different optimization techniques. So Gauss-Newton is, I guess, the more basic version. And it uses finite difference to approximate the Hessian. It's quadratically convergent in theory, but it scales very poorly because you need to do one forward solve per material degree of freedom. So if you have a whole brain, that's terribly expensive. Conjugate gradient is better in that regard. You only need 2 forward solves per step, but it converges more slowly. And like in reality, you wouldn't convert the entire brain as one volume. You would subdivide it into subzones that are overlapping, and then you would optimize those individually and then put them together again. Because otherwise it just becomes so expensive. So how I'm verifying this currently is to have some material field. Here is just Gaussian distributed. And then I generate a field, and I just call this the measured field, even though I don't measure it. And then I do the nonlinear inversion algorithm to get the material field, and then I just compare the results to what I started with. And if they match, then I have some convergence into the correct field. Here are some examples of a Gaussian field and then an inclusion phantom and iterations over, the objective function over iterations for both of them. This is using Gauss-Newton. You can see the y-axis is logarithmically scaled. And I just set some like arbitrarily stop condition. But yeah, it converges and it produces the same field. And for the future, the goal is to actually get like full 3D inversion going, and also to expand the material models to anisotropic models, because the brain is not as isotropic as we would like, and also poor elastic material models, because the brain tends to have a lot of fluid, and also deep learning integration, because people want to do that, and who am I to stop them? I also did this little UI just for fun. Yeah, I think that's it. I want to thank you for your attention, and also to my supervisors, who are really nice. Thank you.
So thank you for a great talk. Are there any questions from the audience? Henrik?
So I saw in your pipeline you had this smoothing step.
Yeah.
Consider to instead add like a regularization curve to your cost function.
Yeah, it has been done by other people and also by me. It's complicated because like when you do this subzone thing, you kind of, there's this inherent like boundary. You can kind of see it actually if you, how do I go back? if you look here, it's like a little bit patchy. So we have looked at Tikhonov and total variation regularization, which like it works, but the implementation becomes so much more complicated that I don't know if it's worth it. But if you want to work on it with me, then you know.
You mentioned the Gauss-Newton method, and you said it's difficult to compute because you need to do finite differencing. But I see that as a slightly separate issue because you're slightly conflating the method that you use to find an optimum and the way by which you calculate the derivatives of the thing that you're trying to minimize. And if you look in the literature, there's a lot of research from people at UT Austin that when you use Gauss-Newton with adjoint methods for calculating derivatives, it works extremely well. So I think you should look maybe a little bit at how you're calculating derivatives and adjoints and separate that from the underlying method which you're using to optimize the problem.
Yeah, no, I agree. We have been looking at that. I think for us, one major thing is that this already implemented method, we kind of have to start by recreating it in some sense, and then kind of optimizing the optimization.
But if you use FEniCS adjoint, which
yeah,
Pepin has done some work on recently, or you switch to Phi-Drake that has very good adjointing already, you'll just be able to get this adjoint out very straightforwardly, in my opinion.
I would also say, especially for the problem that you're solving, you could also just use UFL directly to do the adjoints. But for the problem that he's solving, I think you could just do UFL derivative, UFL adjoint without any problem. This is not time dependent, it's not a stack of equations.
Yeah, we have some examples that we can send you for doing the adjoint and also the second order adjoint purely in UFL.
Yeah.
And Jürgen has these as well.
yeah, I have implemented the joint solver as well. So, but I would love to get some more code. Yeah.
Remy?
Thank you very much for the talk. Very interesting. Have you considered experimenting with derivative-free techniques for your optimization, like Nelomede, or you can say no. That's fine.
Yeah, I mean, so I haven't like, we're a group that's really like medical imaging focused. So I haven't really got into how the optimization as much as I would have liked. But I think once I get this to actually like work, that's the first step, and then I can actually make it good.
If there are no more questions, I think we should thank the speaker again.